Okay. 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 So now getting down to the quality control. Okay. So quality control for control charts. So for control charts, we have C chart, which is for number of defective chart. So it's a number of defective uh, chart. Then we have the other chart here, which is the P chart. The P chart is the percentage of defective chart. So this one is on percentage of defective chart. Then we have, of course, the other chart here is our X bar chart. Okay, so X bar chart. Then we have the R chart. Okay, so these are the control charts that are used in quality control. And of course, um, getting down to the question here. Okay, so for this question paper, the question reads, okay, so we have the question where we simply say, in an effort to improve safety in their plant, a company decided to chart the number of injuries that required first aid each month. Approximately the same number of hours were worked each month during the during 1 year. A large amount of holiday leave was taken by permanent employees during the month of July. Consequently, untrained casual labor and excessive overtime were used to achieve the normal number of hours worked for that month. In April year two, the company replaced the wire basket for carrying and storing of parts and tools with ones made of plastic as a cost-cutting measure. The table below contains the data collected over a 2-year period. Okay, so number of injuries in year one, number of injuries in year two, use appropriate control charts to analyze the data. Okay, so meaning that for this one, we are supposed to, okay, so we are supposed to analyze the data for these two. Okay, for the 2 years, year one and year two. Okay, so now the getting down to the first year, we have this information on this one. So meaning that when finding the C bar is equal to summation of C over N the number of defects that are supposed to be there. So meaning as we get the first one will be 6 plus 2 plus 4, okay, plus 8 plus 5 plus 4 plus 23 plus 7 plus 3 plus 5 plus 12 plus 7. So it's 86. Then 86 divided by 12 is actually going to give us, so 86 divided by, okay, so we have 86 divided by 12 is 7.1. So meaning as we're getting down to 7.17, okay, so that is what we have. So 7.17, this is the number of injuries, okay? So then getting down to the lower control limit. So our lower control limit is equal to C bar minus C3, which is standardized the square root of C bar. So C bar is 7.17 minus 3, the square root of 7.17, which will be equal to, okay, so after getting down to the square roots, 7.17, okay, by 3, and 7.17, so it's giving us the value that we need to calculate. So meaning, as we are getting down here, we are getting down to the C chart. C chart is a number of defective, so number of defective chart. So that is on the C chart. Okay, so here we have gotten the center line is given by this 7.17, and then of course we have the month from January to December. So this is lower control limit. This one is called lower control limit. Then the other one is upper control limit. So upper control limit. Okay, so finding the lower control limit, 3 is a 3 sigma limit, and is standardized. Okay, so we are getting the lower control limit as negative 0.86 or 0. It gives a negative, then it means 0. Upper control limit is the C bar plus the 3 square root of C bar. Upper control limit is 15.2. So where C bar is the center line, or you can even say the average for C chart. And then lower control limit presented by LCL. Then the upper control limit is represented by UCL. So you have the lower control limit, you have the upper control limit. And for injuries in year one, the process is not in control because July has the number of injuries above the upper control limit of 15.2. It is outside the boundary. So this is about what we are looking at, okay, concerning the question, this question, all right, that we are looking at, okay. So we have to do the same way for year two, okay, to find the upper and lower control limit for number of injuries in year two. Okay, so what happens here now is that we are getting down to so here after plotting, we have this one for July, it's outside control limits. Okay, so we are plotting January using the respective data set, which is 6, January 6. We have also 2, 3, 4, 8, 5, 23. So July 23 is above the control. So this is why we are simply saying that it's outside the boundary after looking at the control limits. So July 23 is actually above the upper and lower control limits. Lower control limits is 0. Upper control limit is 15.2. So 23 is outside the interval. Then for number of injuries in year two, the same way we have to find the C bar. C bar is the center line. So we have this as our center line, which is 3.92. The lower control limit is negative or is equal to 0. It's negative. Upper control limit is 9.86. Then we plotting here for the process for injuries in year two is not in control because January number of injuries above the upper control limit of 9.86. So the process was not in control, getting down to with both years, year one and year two. The center line is a 3.92, and then upper control limit in this case was 9.86. And of course, we are getting down to our center line, which is this one or 0. Okay. When it's negative, we will locate it at 0. So this is what we have concerning for the 2 years. So year one and year two, we have those ones. Okay. So that answers question number 1. Okay, question number 1 was on a control chart. It was on control charts. All right. Then getting down to question 2. Question 2 was on cost of quality. This one was on cost of quality. So under cost of quality, we have the first one is prevention. We have the prevention cost. We have the appraisal. internal failure. We also have external failure. So these are the four costs of quality that we actually consider: prevention, appraisal, internal failure, and external failure. So we need to look at this question too, where we need to categorize the costs. Recently, this company received a report from the external consulting group on its quality costs. The consultant um, reported that the company's quality costs total about 21% of its sales revenues. Somewhat shocked by the magnitude of the costs, Bill Marks, president of the gas company, decided to launch a major quality improvement program for the coming year. Management planned to reduce quality costs to 17% of the sales revenues. Although the amount of reduction was ambiguous, most company officials believed that the goal could be realized. To improve the monitoring of the quality improvement program, Bill directed Ms. Holding, the quality controller, to prepare monthly performance reports. Ms. collected the following: actual sales and actual quality costs in first quarter of the following year. So these are the cost of quality. And of course, the sales was this was the sales revenue. So this was the sales revenue. Now we need to, I think, reorganize the quality costs reported so that quality costs are grouped into one of the four categories of the PAF model, which means we have the prevention, the ones which are here in terms of prevention, then in terms of appraisal, in terms of internal failure, in terms of external failure. So these are the four costs of quality that we actually look at. All right. So we need to reorganize, and then we actually, after that, comment on the company's process in improving quality and reducing its quality costs. What advice would you give the company? Be quantitative. Okay, so now from here, we need to categorize these ones in four groups. So categorize costs into four groups. Okay. So under this one, what goes on is that the first aspect here that we need to look at is the prevention cost. So meaning getting down to this one, on question 2, we have the cost of quality category prevention. We have quality planning, 2,500. New product development is quality training. So these ones, the total was 4,200. Okay. Then from here, these ones were coming from so the first one, we are talking about quality planning. So quality planning is prevention cost. The new product development is also prevention. Then we have quality training is also prevention. Okay. So those ones. So from the what we have here, we can just get them from here. Quality planning is prevention. So this is prevention. Okay. So quality planning is a prevention cost. Of course, we have quality training, quality planning, quality training. These are prevention. Then, of course, new product. New product development is also prevention. So this is on how we've gotten to this one. Then getting down to the other category. The other category concerning the cost of quality is appraisal, incoming material inspection, incoming material inspection, product acceptance. You have also field testing. Those are under inspection. So that this one comes to, okay, 30,500 as we are getting down to the appraisal, that is appraisal. Okay. So from here, what we are simply saying is that material inspection, this is appraisal, is appraisal. Product acceptance is also appraisal. Field testing is also appraisal. Then getting down to the other part of cost of quality. Okay, we have internal failure. Under internal failure, we have scrap, which is 12,500. Retesting, 7,000. Downtime, 5,500. Rework, 11,000. Total internal failure cost, 36,000. Okay. Then we have the other aspect where we are looking at external failure. Under external failure, we have warranty, which is 17,500. Then the allowance for warranty, 8,500. Complaint adjustment is 2,500. So meaning that the total cost comes to, all right, we have 4,200 for the total prevention cost, 30,500 for appraisal cost, and of course, internal failure cost is 36,000, external failure 28,800, 28,500. That is for the external failure cost. And the total cost comes to 99,200. Okay. This is what we have as the total cost of quality. Total cost of quality. Okay, so total cost of quality, we have that amount, 99,200. Now, here, the percentage is 4,200 divided by 99,200, which is 4.23. 30,500 divided by 99,200 is 30.75. 36,000 divided by 99,200 is 36.29. 28,500 divided by 99,200, 28.7. The total comes to 100. So from the above cost of quality report, appraisal and internal failure costs are very high. So we have appraisal and internal failure cost. So appraisal and, okay. So appraisal and internal cost are very high as compared to prevention cost. Okay, so the appraisal and internal failure, these two are very high as compared to the prevention cost. Okay. And this clearly shows that companies more inclined to appraisal as a means to ensure conformancy. Okay, the appraisal does not build quality in a product, therefore the company should consider investing more in prevention measures. So appraisal does not build quality in a product, okay? Therefore the company should consider investing more in preventive measures. So this is on this kind of conclusion that we need to make from here. The question was saying that what conclusion can we give, or what advice can we give the company? Okay, so we just reorganize the cost of quality, and then of course comment to the company progress in improving quality and reducing the quality costs. Be advised, what advice would you give the company? Be quantitative. Okay, now there's again some addition that we need to make here. The company's progress in improving quality and reducing quality costs of sales. So sales minus total cost of quality, so meaning 550,000 minus 99,200 as the cost. Okay, and then this was sales. All right, so meaning that from here, so you have the sales here, cost of quality. So we have divided by this of 81.92%. Now reduction from 100, we are simply reducing from 100%, it's 18.08%. Okay, so the 100% is the total percentage. Percentage is always over 100. So percentage is always equal to 100%. Okay. As we calculated this one, the percentage was 100% from here. The percentage was 100%. Okay. So now you are simply saying the government progress in improving quality and reducing its quality costs of sales. We have this one where we're saying 81.92%. is always 100. So reduction from 100 is 18.08%. Since for the coming year, management plan to reduce quality costs to 17% of sales, meaning that the deviation from 18.08 is very minimal, which is 1.0%. The calculated figure is within 17% stated by management. Okay, so therefore, the calculated figure is within 17% stated by management because the 1.0, okay, the difference is very, very minimal. Okay, so what is happening is that for the company, management plan to reduce the sales, so the figure calculated is within 17%, so management can rely on the figures that were found. Okay, now getting down to question number 3. Question 3 of this paper is actually talking about the specification limits. Okay, so this one is actually talking about specification. So we have what we call specification limits. So we have the upper specification limit, and of course, okay, upper specification and lower specification limit. So you took a team of mechanics through the process of using control charts to determine the process capability. You applied the studies to a process that is in a statistical control and output is normally distributed. The specification for the product process are 28 positive or negative 2. So from here, we can find the, okay, so we can find the lower specification limit, which is equal to 28 minus 2, which is equal to 26. Then upper specification limit, 28 plus 2, which is equal to 30. So these are the upper specification and lower specification limit. Now, is the process capable? If not, what proportion will meet specifications? And of course, what adjustment would you make to the process to improve its performance without change its standard deviation? With the adjusted value, determine the process capability and comment. Okay, then the mean from here, the X bar in this question is actually equal to 28.6. Then the standard deviation is actually equal to 0.53. So this is the standard deviation, and this is the mean. Okay. So from here now, what is going on is that we need to find the process capability index and the process capability ratio. We need to find the CP and the CPK. Okay. So we have the the aspects where you need to find the CP and the CPK. So from this one, what is going on is that as we get down to the as we get down to the CP and CPK are the two common indices of process capability. Okay, so we have the CP and the CPK are the two common indices of process capability. CP stands for process potential and it measures the ratio of the specification range to the process variation. A higher CP means that the process has more potential to meet the specification, while CPK stands for process capability, process performance, and it measures the ratio of the distance from the process mean to the nearest specification limit divided by the half of the process variation. Okay? A higher CPK means that the process is more capable of meeting the specification. So getting down to the process capability ratio, so CPK is process capability ratio. So CP, this one is process capability so process capability ratio. Then this one is process capability index. So this one uses this 6 sigma. So this one uses the 6 what? 6 sigma limit. Okay. So this is what goes on. So finding the upper specification limit is 30, lower specification is 26. Substituting here, we have 1.26, okay, as the process capability ratio. So this one is the process capability ratio. So process capability ratio. Okay, so we are getting 1.26. Well, the process capability index. So this is on process capability index. We are getting the minimum of using the formula here, upper specification minus the mean over 3 sigma. This is 3 sigma. Okay, so after this one, we are getting down to the minimum. So it is 0.88. So using the CPK, the process is not capable because 0.88 is less than 1. And for CP, the process is not capable because the CP 1.5 is less than 1.5. Okay? That may be acceptable for some processes. So CPK, for CP, the process is not capable because 1.26 is less than 1.5 that may be acceptable for some processes. Okay? So this is the one we have. Okay? So from here, the proportion meeting specification, we use the the Z calculated now, upper specification minus the mean over standard deviation. So you have a 2.64 and -4. We're using the statistical Z tables, plotting here on this one, we are getting the proportion meeting specification is approximately 50%. Okay. So the following are the adjustments to be made to the process to improve performance. Adjusted mean will be 28.6 minus 28, which is 0.6. Mean needs to be adjusted by 0.6. Okay, so new mean should be 28. So new mean should be 28. Okay, so the new mean should be 28. That's what it means here. And the process capability index now, in this case, so for the index to be the minimum of upper specification minus the mean, which should be 28. Okay, then the mean should be 28, so meaning that the CPK is 1.26, 1.26, which is greater than 1. Okay, meaning that the process is now capable of meeting specifications. The process is now capable of meeting the specifications. Okay, it has given us the same values. Okay, it has given us the same values here, 1.26 and 1.26. So meaning that the process is now capable of meeting the specification for the CPK is above 1. Okay, so from here, the CPK was less than 1. Okay, initially CPK was less than 1. So the process was not capable. It was less than 1 initially. Now, after adjusting the mean, okay, the CPK is now above 1. So meaning that CPK is greater than 1, meaning that the process is now capable of meeting specifications. So this is how this paper, this question was supposed to be answered. All right. And then here we are just getting down to the probability proportion meeting specification. We found 49.59, which is approximately 50% of all proportions. Okay, make the specification. Okay, proportion meeting specification 50%. All right, so this answers question number 3. Okay, of course, for this one, we had to find the CP. Okay, CP is equal to process capability ratio. Process. Okay, so this is process capability ratio. Okay, we have this process capability ratio. Okay, so and then the other one is the process capability index. So this is the capability ratio. All right. Then this other one, CPK is equal to process capability. Okay, so process capability index. So this is what goes on here. So this is what we use when you are testing for the process capable. So we use the CP and the CPK to test the process capability ratio or the process capability index. So this marks the end of this paper. Okay, for the questions that came in this assignment paper. Okay, so the question 2 was cost of quality. So this one was on cost of quality. And then the first one was on control charts. Then the last one was on specification uh, limits, question 3, which was testing for um, process capable of meeting specification. Process capable of meeting what? Specification. So process capable, okay, of meeting specification. Okay, so this is it, what goes on this paper. All right, so we end the class for now.